Alright team, so we've looked at how do we make radioisotopes, what are radioisotopes. Now we're going to look at how do we detect them basically. How do we detect radiation? What equipment do we use? What should have the Hulk had around the lab to prevent his overexposure to gamma radiation in the first place? Alright, so what's the point? Basically, by the end of this, you need to be able to describe the processes used and the tools to identify radioactive sources in 4 instances. They're not too hard, and you can probably tabulate them, in a way that goes, I guess, process, tool, and what description, if you want. I mean, it's up to you. So, here's a guy called Wilhelm Röntgen. Now, it's Roentgen. There's probably a couple of umlauts or something in there anyway. And he is a German physicist. Interesting to know that we call them, most English-speaking countries call X-rays X-rays, but a lot of the world calls them Röntgen rays. And the reason they call them Röntgen rays is because this is the guy who discovered X-rays, and he discovered it by having an X-ray source there and having photographic film just sitting next to it, and it captured pictures of his hand, or his wife's hand, I think was the first one that he did on a person, but it also captured pictures of keys, I think were the first things he sat next to it, whatever, it doesn't matter. The whole point is that photographic film reacts with radiation, which we'll get to in a second. Okay, so the Geiger Counter. There's a slight error with our diagram here, and this one, there's a better diagram coming up, so if you need one to draw, this is not it. There's a better one in a second. There it says cathode, that should say anode, and that should say cathode. Alright, so basically it's a metal tube attached to a DC supply filled with argon gas, which is a noble gas, and because it's a noble gas, this means it's stable, it's in there, it's not reacting to anything, it's inert. Now, as radiation enters it, it's what we call ionizing radiation. So alpha, beta, gamma are all ionizing radiation. So as the ionizing radiation enters, it goes through this mica window here, which is a type of glass. It's actually a type of rock, but it's kind of like glass. So the mica goes through the radiation goes through the window, hits a hits an argon atom, ionize it, which means the electron leaves, and that electron then leaves that and completes the circuit. So because that leaves and is attracted to the cathode, it will complete the circuit. And when that happens, it sends an electrical pulse along the wire, and it hits either an amplifier or a digital counter, or both, and will either make a click sound or it will put a 1 up there. And the faster it goes up, the more radiation there is. So the more radiation that enters, this number or the frequency of clicks will increase. This is just a little bit, it will click over slowly. And there is always background radiation. That's actually the first thing you see when you pull out a Geiger counter for the first time, is that it still just sits there clicking constantly, but slowly. So, as we said, basically the amplifier increases it, blah, blah, blah. This is actually a pretty good picture. I like this one. Here we see cathode, anode. It comes in, the electrons are attracted to this is attracted to that, and that will complete your circuit. Alright, so then you got the scintillation detector, which I quite like. We don't have one of these at school, unfortunately. So basically, certain things, when they become irradiated, they emit light, and that's because as an electron gains energy, it moves up an energy level, and then as it moves down the energy level, it releases a photon. Remember, we've talked about this. This is how we get your flame tests. That kind of a deal. So basically, the electrons in these substances, they get excited, they emit a photon as they return to the lower energy state, and this photon receptor down here collects it, and it uses something called a photomultiplier. We're not going to talk about that. If you do physics, gold, you will learn about that in physics, but we don't really have the time to go into how a photomultiplier works. But basically, it's a series of mirrors, etc., and it creates an electrical signal down the bottom here, and yeah, so that's cool. So that each time that signal happens, that means that, so it's also attached to a counter, just like the Geiger counter is. Cloud chamber. This is my favorite. Now, the cloud chamber is basically a chamber, so that's this here, which is a partial vacuum and it's filled with an alcohol. So the alcohol is then vaporized by making it a partial vacuum, so it enters the air. You put a radiation source underneath it, which ionizes the air. Now the ionization of the air causes the alcohol to condense around the ions, and we see vapor trails. We see clouds, and it's pretty sweet. So there's 3 types of radiation. I would contest that most people who aren't trained physicists, including your teachers, can't really, describe which is which with any great clarity. They could probably pick out a gamma vapor trail, but I would say the alpha and the beta ones are at least they're tricky. So, in theory, they're actually very straightforward, but in reality, I think it's a bit trickier than that. So, the alpha could produce short, straight trails. That's because they ionize super easily. Beta produce less dense, and they're longer because they travel further. If we look at if you look at the amount of penetration they've got, that's why, and it's all because of the size of the particles. Gamma produces these long, wispy trails, and they're the ones that you look at and you go, that's quite pretty. We'll see in a couple of seconds. These are actual photos. So here you can actually see the sort. It's rad. Okay, so this is what's happening. Here, these ones here. That's, I would say, this is my guess. That's a beta trail. These ones here are alphas, and these long, wispy, rad ones, they're all your gamma sources. And here we see some more. Again, this is a real photo. They've just changed the colors, given it false colors so that the contrast is easier. And here's another one. So we've got the alpha and the betas. So yeah, I would say that's an alpha. That's an alpha, and that's probably a beta. The whole point is that most people, when they're looking at these, can identify them via a comparison. Then there's photographic film. So we've got Röntgen. He's the guy we talked about earlier. Basically, if you expose photographic film to radiation, it turns black, and this is because silver halides, which is what covers photographic films, are sensitive to radiation. So they darken when exposed to radiation. Now, one thing we can do is we can have these badges. Now, you can wear badges that contain photographic film, and they will show you exactly how much radiation is there. And the whole point is, when your badge changes to the wrong color, that's when you've been exposed to too much radiation and you need to leave. There are lots of scientists, particularly early days of working with radioisotopes. Marie Curie, for example, and her husband, Pierre, who they were just exposed to way too much. And this is the sort of thing which a scientist will have now, that you work in the lab, and if it changes colour, you've been exposed to too much, it's time for you to leave. And you actually get locked off from the lab for a certain amount of time, just until your exposure level drops and everything's cool, and then you get to go back. That's it. That's the way we detect them. So there's 4 methods there. I hope that makes sense. Bring any questions you have into class.